So looking at method of sections, if you've already done method of joints, then method of sections is just another way of kind of doing the same thing, but maybe a little bit less work. The biggest thing to remember here is that if the truss is in equilibrium, then any section of the truss also has to be in equilibrium. So like if I just wanted to look at this section of the truss, it's not like it's like pulsing and changing shapes or anything like that. The entire section is totally in equilibrium. So if I was going to cut that piece of the truss apart, then if I looked at the internal forces, then all of that would still just come out to be in equilibrium. Okay, so there's a couple of ways. So like when we solve this with method of joints, let me label these little points with like stuff. Let's call it A, B, and C. So in method of joints, we kind of did this thing where we would like take joint B and say, okay, so joint B here, that's going to be, we're going to assume everything is in tension unless there's a reason not to. So we have the 500 here. We have the tension BC, and we have the tension AB. And then what we'll do is we'll say, okay, so then that goes with this, I drew it too close. This goes with this, whatever you call this thing, member of the truss, and it's fully in tension AB. And then we just kind of went from there. Well, I'll write the other one, tension AB. And then we'll have this one here that we kind of broke apart. And then this one was in tension BC. And this was the whole thing we did with method of joints and stuff like that. Okay, but the thing is, with method of sections, it's basically the same thing. It's just that it looks kind of different, I guess. So what I could say is I could say, well, let me go ahead and I'm going to break this here. Then what I can say is, so I'm going to kind of cut that, and I'm going to cut this. And then I've got outside that cut. Now, a big deal is that we're not assuming on all these is we can't have any forces coming in on the sides. All the forces have to be applied only at the connections. That's a huge part of this. And that means that this tension here and this tension here, why that matters is that means that there's no shear. Okay, there's no shear. If we had potentially forces not applied at the points, then we could have shear. But that ends up here with this 500 newtons and tension BC and tension AB. So this is technically method of joints, and this is technically method of sections. Now, what's kind of stupid, seemingly, is that whenever you're looking at this, the equation that you would get here is exactly the same thing as the equation you would get here. And that's just because we looked at one section. We sectioned the single joint, if that makes sense. So we actually don't end up with anything any more interesting. But what we can do is instead of sectioning it there, instead of looking at the top section, let's pretend that we only cared about the bottom section for whatever reason. Now the reason, I'll give you a reason why we might care about that, but let's see. If I'm looking only, so this is top section, and now let's look at bottom section. Okay, so for bottom section, we're going to do cha-choop, 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 cha-choo, and then this is going to come like this. Okay, and then I still got my pen, and I've got a ruler. Okay, so now I have to pay attention to my reaction forces, which I could totally have gotten by doing an examination of the system level. So I can just go ahead and I'll write those in. So this one is going to be 500. AY, as I've got it drawn, is negative 500, and AX is negative 500, as I have it drawn in. Okay, so I've got those values plugged in there, but now what I have here are the tensions in AB and the tensions in BC. So I guess one thing I should make sure that you see is if I'm taking this dude here and I put it over here, those the TAB cancels out. I can't show everyone, but that TAB cancels out and the TBC cancels out. So those become internal forces again when I throw this together, and all you see are the previous external forces of the reactions at A, the reaction at B, and that 500. Okay, and that's a huge thing. Now, what I could do is I could go ahead and I could solve this problem as I've got it here, and you're like, well, I don't know what these distances are. I don't really need to know those distances because this is collinear with, well, it's supposed to be collinear with that point. And I do know that this distance here is 2 meters. So what that means is Now, okay, so I promise I'd tell you a reason why we might do this. The reason we might do this is, let's say for some reason this is a much more complicated structure, and I don't actually need to know the tension in this one, but I do need to know the tension in these two. So what I can do is I can draw my section through the beams that I'm interested in, and then only worry about finding what those values are. Okay, sort of. Okay, so what I could do is I could say, okay, so what I'm going to do is I'm going to take the moment about C, okay, and if I'm going to do the moment about C, then let's see, this dude here is collinear, and this dude is collinear, and that's collinear, so I don't need to worry about any of those moments. The only thing that causes moments here would be the negative 500, so it's really pointing down, so that's a positive 2 times 500. And then the TAB is going to be a negative moment. So a negative moment, TAB, times the distance 2 as well. And that's going to be equal to 0. So I've got minus TAB. I know this is a dumb example because it's 2 TAB is equal to 1,000 because, you know, it's obvious, but if you can't understand the obvious ones, you can't understand the unobvious ones. Okay, so now we get that the TAB is equal to 500. So the thing is with method of joints, the only way to get a lot of these problems, the only way that I could have gotten TAB here was to find TBC and then TAB, you know, because of some of the forces in the X had BC and AB is unknown. So I had to solve both of them. Now, if I happen to be in a situation where I only cared about the 500, I'd actually be done already. If I happen to want the TBC, I could do the sum of the forces in the Y direction on the system or in the X direction on the system. So let's do the sum of the forces in the X direction because I'm feeling it. So in the X direction, I've got negative 500 coming from here. So that's my negative 500 coming from there. And since this was a 45-degree angle, that would be negative root 2 over 2 TBC. And I can work through that, and I can get that TBC is equal to negative 707. So that means it's in compression. So I'm still able to get the same answers. The difference is that with the exception of this one I put over here because I was just trying to show y'all stuff. Generally, when you're doing method of sections, you've got dimensions, so you can use that moment equation. When you're doing method of joints up here, there's no dimensions. Everything is either everything is collinear, or it's concurrence, which is also collinear. So there's no way to use that moment equation, and that's one of the benefits of using the method of sections is you can actually use those dimensions to take advantage of it. So again, the biggest thing about method of sections is that you can just draw the line through whatever you're most interested in and just kind of take it from there. It's one of those things that some people are just like hardcore method of sections, some people are hardcore method of joints, but really both methods work, and usually on an exam it'll say something like use method of sections to blah, 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 or use method of joints to blah, blah, blah. I guess the only benefit of method of sections is that we're starting to get you ready for the idea of internal forces.